So thank you very much, Mr. Chairman. And many thanks to the PPAM conference organizers, particularly to the organizers of this very workshop for giving us the opportunity to present some of the results my colleagues and I have achieved on the subject of wildfires in the Hidalgo 2 project. I hope you find that interesting. My name is David Caballero. I represent the MetroGrid team. MetroGrid is an SME based in Spain whose core business is focused on applied meteorological and climate services, more particularly related to natural disasters and forest fires. We MetroGrid, we have been providing this atmospheric dynamics modeling and wildfire simulation for many years in Spain, for several decades, and with some international experience as well. MetroGrid has a specialist in atmospheric dynamics modeling and wildfire simulation, such as my colleagues, Lady Laura Salazar, which is with us today, and Luis Torres as well. And we have also computer and system engineers like Angela Rivera, who is providing us the support. All of them are represented here today. So you know that wildfires have become a global threat in recent years. You know, we are witnessing, even today, we are witnessing highly destructive events with phenomenal energy release, leading to these intense interactions with the atmosphere, resulting in phenomena that are very, very difficult to predict. Current models that we are using barely account for this fire-atmosphere interaction, partially due to the high computational demands of these thermal fluid dynamics modeling wildfires that requires. It is not just the flame front what we are concerned. It's also the smoke emission and dispersion, which is phenomenal. Has been a big concern, a global concern, due to the effects on health and the key service, such as transportation. Well, the idea is that we have been, this modeling challenge has been addressing the wildfire pilot study on the Hidalgo 2 project. We aim at to simulate fire spread, fire atmosphere interactions, smoke protection, and how these affect the landscape at the landscape level, large regions of the territory. In additional, a more detailed scale, we'll explore how fires can impact populated areas. And finally, help with the ultimate target for helping to raise public awareness and to contribute to firefighter training of wildfire scenarios. Well, this pilot study therefore focuses on two scales: the landscape scale, which is large areas of the territory, which center the study on the fire atmosphere interactions over large areas of the territory, and the populated area scale, the urban scale, to study more detail how flames and smoke can affect the population and buildings. Both scales require a specific approach, models, and a level of detail. For the landscape scale, we have proposed a workflow that allows efficient wildfire simulation of this HPC infrastructure, which can be implemented in firefighting service operationally. Is our ultimate target, is objective, is to implement that operationally. To achieve this, we have outlined a description of the study area and all the necessary data, and we have the pre-processing of this data before the computing and the subsequent use of the mesoscale atmospheric models like WRF, coupled with fire simulation models like SFIRE. With all these, we have also proposed coupling some kind of pollutant dispersion simulation coupled with these models like CHEM. All models have these computational domains that are perfectly coupled with these different grids interacting and consistently setting appropriate resolutions for each of one. That's quite challenging, is what we are trying to achieve. This requires a significant effort and design the simulation computational domain. Well, we are using some of the EuroHPC network infrastructure, such as Vega, Lumi, and Meluxina, to proceed with some preliminary working on that. So these simulations designed requires, as I told you before, requires working with high resolutions making it necessary to perform downscaling of the atmospheric dynamics modeling. This downscaling involves nesting up to 5 computational domains with increasing resolutions, which shows the mesoscale atmospheric model WRF as a base for the atmospheric dynamic simulation, and the fire spread model is SFIRE. And both models are working in a coupled manner, so they are interacting between them. Calibration and test simulation has been carried out in the central area of Iberian Peninsula. In particular, this Madrid region in central Spain, in which we have had several significant wildfires within a radius of 40 kilometers, which is quite a dense type of significant fires. The simulation involves, as I said before, 2 computational grids that are perfectly coupled. On one hand, we have the atmospheric grid, which is represented here with this pink color. In this case, we have used a 200-meter resolution. On the other hand, we have the fire simulation grid, which is 10 times higher resolution, or 10 times finer than the atmospheric grid, and they are perfectly coupled. The final computational domain is then divided into tiles. That's the key point of parallel computing. This division into tiles, each one comprising 10 by 10 atmospheric cells, or even more. This division allows this parallel distribution of calculations on MPI architectures. An additional one cell-wide halo must be described to allow the computation or the communication between the different tiles in this parallel computing approach. So one of the challenges, the biggest challenges, my colleague Lady Lauda can speak more on that. One of the challenges has been to achieve atmospheric grid resolutions below 1 kilometer, finer than 1 kilometer, which is required studying strategies and several parameterizations that we have done to obtain consistent and reasonable realistic results that we have here. Here's an example at your left that we have the typical 100 or 1 kilometer resolution of the atmospheric grid. And what we have achieved is 200-meter resolution with some planetary boundary layer configurations. That's a big challenge for that. Then the fire spread simulation has been coupled with atmospheric modeling. What you can see here in black is the fire front, and the head is at your left, and the rear of the fire is at your right. So we couple this atmospheric modeling with the fire spread, specifically the heat flux and moisture which is injected into the atmospheric dynamics, which in this case is divided into 40 vertical levels. Additionally, the effects of local induced winds feed back into the flame from the spread simulation, creating this feedback. So the flames create this circulation, which at the same time feedbacks into the fire. Here you can observe some wind convergence in the head of the fire and some vorticity at the head of the flame front. We have to tell that all this occurs in a volumetric computational domain, a 3D computational domain. So vertical interactions are very relevant, particularly all these with upward and downward convective movements, which are creating this particular behavior of the fire. Both what we have the vector fields, the 3D vector fields, and the 3D scalar fields, like temperature, pressure, and so on, are stored at its time step for advanced visualization. The time step that we are using is 1 minute. Not for calculation, it's just to export the results, is 1 minute. We have carried out a series of simulations in central Spain, as I told before, particularly in the Madrid regions, just in the center of the Iberian Peninsula, where within a radius of 40 kilometers, we have experienced several significant fires, and more particularly this one, the Almorós Cadalso fire in 2019. We have picked this one, particularly for its significance. My colleagues have performed several simulations in HPC resources. Changing the designs of the computational domain with and without these vorticity calculations of the less calculations for the vorticity. But also we have tested more than 20 configurations of the planetary boundary layer, PBL, modeling to explore the reliability of the results and compare it with the less. given that we are going between 1 kilometer and lower, 200 meters, we have kind of a gray area in which both models have some limitations, the PVL and less. So you have to explore more on that. We have confirmed as well the importance of the simulation, the interaction or the feedback between the fire and the atmosphere to achieve very realistic results. These are the simulations that we have carried out. The Almoroz Cadalso wildfire was quite significant because it's the largest recorded in Madrid autonomous region, exceeding 3,000 hectares. It started in June in 2019, just before the COVID pandemic. The initial hours saw a very rapid spread, which were driven by the wind, basically, southeast winds, 25 to 30 kilometers an hour and gas up to 40, 50 kilometers an hour. One significant fact is that there were no firefighting in the first hour because of it was in the limit between and the border between two different communities. So there was some confusion there. So it was 1 hour running free, and then up dances towards populated area. We have this synoptic wind decreasing at the last part of the afternoon or in the night, leading to topographical behavior. We have very strong wind, so the smoke plume remained very low, touching the ground and affecting nearby populations. Here you can see the actual progression of the wildfire, as recorded by the Castilla-La Mancha Wildfire Suppression Service. The rapid expansion, the first hours was really, really big. You have to think that this is about 40 by 30 kilometers. And the rapid expansion, the first 3 hours, about more than 3 kilometers in 1 hour. No, sorry, 6 kilometers in 1 hour. And then we have this rapid expansion in the first hours, and these are the first hours that we have simulated in the HPC installations. There's a view of this fire, which was primarily driven by the wind, and we can observe the smoke plume that were very low, touching the ground, close to the ground, with the fire perimeter remaining very elongated and narrow. This is a typical wind-driven fire. You have to think that these were grasslands, very pure dry grasslands and sparse shrubs. It exhibited at high energy release, especially in the head of the fire. So we have prepared this design of the simulation, 4 nested domains from 1 to 4, with atmospheric data as boundary conditions. It was ERA 5 reanalysis. So we creating these dimensions of 233 kilometers of the domain 4, which is the inner one, to 221 kilometers at a resolution of 200 meters, as I mentioned before, and spanning over 45 levels, vertical levels in the atmosphere. So we have about 58 million cells for the atmospheric modeling and about 128 million cells for the forest fire simulation. We use the LUMI cluster, 8 nodes of 128 cores, of total 1,024 cores, and the computation time, the average computation time was about 1 hour and 45 minutes. We extracted from the Forest Fire Service of Madrid's region all these forest field maps using the behave field models, but we did not model in the crown fire because it was in the second and third day taking place. So we basically what we simulated was the surface fire at its spatial resolution of 20 meters. We apply the simulation. As you can see the comparison, what we see in color, and this color is the warfare fire simulation in the HPC cluster. In white, you can see the typical simulation done with the typical models without fire atmosphere interaction. And in red, you can see the final perimeter of the fire. You can see the progression. In green, you can see this line is the real fire progression. It's very close to the simulated with this fire atmosphere interaction, very close to reality. And it is exceedingly less under predicted by the typical forest fire simulation like the FCA or Behave or Farsight or Wildfire Analyst. So This is telling us that it is super important to account on these forest fire and atmosphere interaction. Here you can see the final perimeter at this time and the simulated perimeter at this time, which is way more accurate to what we obtain with this simulation of the typical forest fire without this interaction. And again, we have a 19 hours UTC, exactly the same. So you can see that without feedback, we have under prediction. With feedback, we have very close to the reality in the axis, the size, and the shape of the fire. That's very, very good news. So the results of the simulation is that basically we have, without fire atmosphere feedback, we are similar to those obtained with the traditional models, but without feedback, we have a significant under protection. With feedback, it's very good match with observed reality. With a slight over prediction of fire front, but it's very, very clear that it's a matter of configuration and the type of forest fuels that we are using. It's highly sensitive to the initial data. We have not good data as border conditions. We have not good simulations. And we have this calculation gray area between PBL and less, adding some uncertainty to the wind configuration. We have also calculated the smoke protection dispersion, volumetric using passive tracers. We have an evolution of the smoke. I prepare something for you as well, which is this simulation. And you have here 6 hours of simulation. Every frame is 1 minute, so it's a big compression rate. You can see here the volumetric simulation of the smoke spread, including the optical response to the smoke integrated in Unreal Engine. We have some other simulations integrated in the session service. This compression rate has been a little bit less. It's every frame is 24 minutes, but you can see the actual position, the vertical position of the wildfire simulated in these HPC clusters. All this has been integrated in Unreal Engine for virtual reality analysis. We have some data about scalability, although these are very preliminary results. So we cannot drive very relevant results in terms of scalability. We can see very clear we have a pre-processing phase with 3 different stages that capture most large portion of the execution because it's done in 1 node. As we are creating more complexity of the problem, larger scales with more tiles, this phase loses significance in comparison because we have clearly that we have a comparison between the speed up of world-first fire simulation compared with the number of nodes. With this dynamic downscaling, there's a clear decrease of computational time with more nodes. We are planning to use this approach up to 20,000 cores. And here's the more or less the scalability with these preliminary results, although they are no significant. With some constraints and limitations using the HPC, we have listed them in this publication, but it's important to say that we have it is not a bottleneck, but it's reducing the computation time. It's this communication overlapping of the regions. And the design of the domain is clearly affecting the effect on the performance. Also, we have to explore other sources of more detailed data as well. We have also observed that depending on the machine that we are using, or the cluster we are using, we have different peculiarities. So we have to reorganize the whole simulation. So it creates kind of non-standard way of working with the HPC installations that should be solved in the future. Just to end my presentation, may give you some look into the future. We are creating ensemble simulations, piling up all the simulations to obtain this burn probability map. We have already done some examples with 10,000 simulations to obtain which is the probability of pass of the fire. And finally, the final slides goes to the visualization. For us, it's as important to integrate all these complex data, dynamic data, which is moving in time, into proper advanced visualization, integrating the output of the simulation as standard file formats, particularly this VDV for sparse volumetric data into visualization platforms like Unreal Engine. Let me show you just for ending this with a nice video, which is what we have achieved integrating these fluid dynamic simulations into Unreal Engine for simulation of real cases of fire and smoke. Or our latest integration is with Cesium Service, so we have very precise position in a 3D realistic environment like this Google Earth 3D environment. So as conclusions, may I just mention that wildfires are a growing concern. Their behaviors become more and more extreme. So simulation requires significant computational capabilities. The use of HPC absolutely allow greatly progress in this area, but making it operational for firefighters is still a challenge. It is necessary to continue exploring modes of configuration that better reflect reality and reduce uncertainty, particularly this range between 1 kilometer, 200 meters. We have this great area that we have to explore, and to include data simulation in HPC processes for incorporating new real boundary conditions and reducing uncertainty simulations. And in the future, we are exploring within the Hidalgo 2 project as well, the use of artificial intelligence inference engines to improve the operational use of these simulations as well. May I conclude by telling that advanced visualization results of these very complex simulations is just as important as numerical simulation for awareness and training. Well, I hope this has been of your interest, and I will be very happy to take some questions. Thank you very much.